Good morning. Let's get started. Hi. Good morning. Okay, so everyone, today we are doing prefix sums and applications, and homework. The homework is released like at 8 a.m. this morning on prefix sums. And homework 2 is due today, but you can submit it until Friday on caching. Is everybody okay on homework 2? Has everyone started homework 2? Okay, cool. Nice. All right. Oh, this isn't working. Why? Okay, yeah. So as a reminder, in about one and a half weeks, we have an exam in class, and this is the prefix sum is going to be the last topic on the exam. So we're going to do what we did in the beginning, like the speed up and efficiency analysis, and we did work span after that, and then we did cache complexity, cache oblivious algorithms, and then today we're going to do prefix sums. And there's not going to be MPI on the exam, and we will do collectives next week, but it's not going to be on the exam either. Yes. Yeah, cache oblivious analysis is like what we're doing on the homework, which is like you divide the problem, but you don't know, like the algorithm doesn't know the cache parameters. Yeah, but you do the analysis with respect to the cache parameters, but the algorithm itself is not. It's not splitting on like M or B. Yeah, makes sense. Yeah, I guess like it's not really like the analysis is kind of the same for both cache aware and cache oblivious algorithms. Maybe they should say like cache oblivious algorithms rather than analysis, because the analysis is using the same techniques. Cool. Questions? Does make sense? So there's going to be 5 questions, at least one in each category, and one more in one of the other ones, depending on what I come up with. So yeah, I will post some like example exams from last year. They copy, I think they cover slightly different stuff. Like they didn't do caching, they didn't really do work span. I remember, like when I looked at their exam, it was just like efficiency and prefix sums. So there are like a lot of prefix sum questions, but I can post some exams from like other courses that are not this one, but that have some questions relating to the other 2 topics. So like not all the questions on each exam will be relating to the topics here, but yes. Yes, yeah, pretty much. In topic, I guess, but obviously not exactly the same. Yeah. Any questions, concerns? Cool. Let's move on then. So today we are doing prefix sums, and this is the definition for prefix sums. So you get as input an array, which is n elements, x0 up to xn minus 1, and the output is an array y of the same length as x, where you get each entry in y is called a running sum, where it's defined with this recursion. Y sub k is, if it's at 0, then it's just the first element, and otherwise it's x sub k. This is a binary, any arbitrary binary associative operator with yk minus 1. So you can see that this is recursion because it's dependent on yk minus 1 for yk. And yeah, this is for all of k minus 1. And binary associative operators include like addition, multiplication. They could include more complicated things, like anything that you might think of, as long as it's associative, and like max, for example. And yeah, do people know what associative means? Okay, great. Okay, so this is the definition. It's pretty straightforward. You just keep track of the things going left to right. And here are just a couple of examples. Basically, you want to fill an array with partial reductions using your arbitrary operator. So you have these 2 arrays, A and B, and using sum, like addition, which is one of the more common operators that you would use for prefix sums, is just adding up the elements going left to right. So like you start with 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 2 is 7, and so on like that. But like I said, you can have other operators, like max is also associative. So if your operator, if you have A and B, then you apply max, and then that would just be like the max so far. So up to here, 3 is the max, but then once we get to 4, now 4 is the new max up until the end. Partial reductions just means the reduction so far from left to right. Yeah. good question. That makes sense? Okay. Yeah, there are a couple of variants on this prefix sum. The one is called inclusive scan, which was the first one that we did, which is when y sub k includes x sub k. In some cases, you may not want to include x sub k when computing y. So inclusive would be the sum that we just did, like 3 plus 1 is 4, like that. And then exclusive means that you just don't include this element that you are at, but you include everything before it. So here would be 0 for addition, the identity for anything else. Yeah, so here, but then this is 3 because it's including everything up to, but not including this point. 4 because should be 7, I guess, because 3 plus 4 would be 7. I'll update it. Oh, yeah, sorry. I forgot those. This is the input, yeah. So it is actually right. 3 plus 1 is 4, but you're not including this one, so it's not 5. Yeah. Yeah, so that's just 2 variants on scan. You can easily get inclusive from exclusive by adding the first element, just element-wise. Like you just, if you had the solution to exclusive, you just add x sub k into each slot. However, it's harder to go the other way because you need operator inverse. Like if you had subtraction, you could do it. You just subtract out x sub k, but not any arbitrary operators don't necessarily have inverse. So this may vary depending on which operator you're using. Okay, and then last, there's another variant called suffix scan, which is just the same. Basically, if you think of prefix sum as left to right, then suffix scan is right to left. So rather, this used to be x sub 0, now it's x n minus 1. So this is inclusive suffix. At x minus 1, or at n minus 1, y is just x, and then otherwise it depends on k plus 1 rather than k minus 1. The algorithms are pretty much the same for both, just in the other direction. Okay, questions so far? Okay. Yeah. So if we were to implement this serially, it's pretty easy. You just write one loop going from 1 to n, and then you do this summation based on yi minus 1 and then x of I for inclusive scan. This is clearly order n, and takes n minus 1 operations actually, because you don't need to do the one at 0. And the ith iteration depends completely on the I minus 1 iteration. So at first, this seems like it would be challenging to parallelize because you have dependency just like one after the other. We can try several things. First one is you put one processor on each element, and then you do like n separate sums. Like each one of the sums is separate, like sum up to 1, sum up to 2, sum up to 3, and so on. You could do those all in parallel. And that would be technically parallel. The span would be log n, because like you would put a parallel 4 on each one, and the span of the longest one is like the length of the longest one is n, so the span of it would be log n because you just put a parallel 4 loop there. However, the work is inefficient because it uses n squared work. The first one uses 1, the second one uses 2, all the way up to n. Sum of numbers of 1 through n is n squared, basically. And this is not great because we want work efficient algorithms. One of the classic algorithms for prefix sum comes from Hillis and Steele, and this is the pseudocode for it. It's really simple. We're going to assume that we have powers of 2 for now, and later on we can relax it to arbitrary numbers. So there's 2 loops. The outer one goes up to log n, from 0 up to log n, and then the inner one goes up to n minus 1. And basically, it just connects like powers of 2 to each other in this circuit. So the first one, you connect elements 1 distance away. Second one, you connect elements 2 distance away, 4 distance away, and so on. What is the work in the span for this one?
Work is n log n.
Mm-hmm. Good. And the span? Log n? So it's at least log n because the outer one is log.
Yeah.
And then the inner one goes up to n minus 1. And in the first one, it's like these pairs, but they could be done in parallel, I guess. Yeah, these can, like every level can be done in parallel, but the levels have to be done serially. So maybe like what is the span of each level?
Oh, explain the algorithm a little bit more.
Yeah. So this is going, I is going through basically you only use I up here basically for powers of 2. So I is basically telling you like you're doing summations of neighbors in some sense, but the distance of your neighbor, like how far are they, like 1, 2, 4, and so on, is dependent on where you are in the outer loop. So like in the end, the last element is basically like the tree summation that we've done before. Like you do pairs and then you do distance 2 and 4 and so on until you aggregate them all into here. And then, so this one is tree summation, and prefix sum is like tree summation, but instead you want more things. You want an entire array rather than one element. So that's why you have to do these additional connections to get you like the correct prefixes. And basically, you can think of these as like at any point, once you've done the levels, like the closest next power of 2 from you contains the summation of all the previous powers of 2 up to that point. Like this is the first element, this is the last element.
Would this span be more than?
Uh,
Because the outer loop can be parallelized, but the inner loop still runs series like at each level.
other way around, you mean? Like the outer loop has to be done serially because the dependencies, like you have to do these summations, you have to calculate these before you calculate the next one because like this one, for example, depends on this.
Oh, correct. Actually.
So it's log n, and then the span of the inner one not like log n as well.
Yes, why is the span of the inner one log n?
That's just like a parallel 4 that goes from that to n, right?
Yes, exactly. So
But doesn't that make it like log n plus log n, and then it's log n?
uh, that would be
Like, I'm
log
hesitant to say
squared.
log squared.
It
Yeah,
is log
I'm
squared, I
hesitant
think.
to say log squared because we talked about so often in the beginning where it's like if you have a big log tree and then you have more log trees on the bottom, that's still just log n.
Mhm.
2 log n.
Yeah, but that was like when there's only one. I guess that was when both of them were parallel, so that would be 2 plus log n. But when this, when the outer one is serial. So does that make sense to everyone? So, oh, actually, why is the span log n? I thought it'd be log squared because the outer one is log, and then the inner one is each log. Is it because they decrease in size? Maybe.
Oh, I thought it was because like so you're keeping the first loop zero, but the second loop is parallelized. So
Yeah.
if you parallelize the second loop, it would be log n. I would say just because of like binary working model, like high complexity of parallelizing a for loop, like it would just be the log of that. So the span is just log n plus log n plus log n.
Yeah. So the span would be like log n, which is the first one. Like the first one is a parallel 4 over size n, so that's log n. Then the second one is a parallel 4 over size log over 2, or log n over 2, because now like the number of sums that you have to do is halved because the distance.
That's the real you're saying, right?
Yeah. Yeah, I think it's log squared because the outer one is log, and then maybe it's log n because this is pram. Yeah, let's call it log squared because it's pram. But in binary forking, it'd be log squared. What do you mean? Oh, in the exam, I will specify which model. Yeah. So in binary forking, it would be log squared. In pram, it would be log because the outer loop is log, and then the inner loop. In PRAM, you can do a parallel for of size n in span 1. So, yeah. The work is still the same in both, though. Okay. Yes.
What is this? Oh, like I plus one is like the level, and then J is the index.
Yes. Yeah. Yeah. Exactly. Because J is going up through n. That makes sense. So this is closer to work efficiency than log n rather than n squared. However, we want n because the serial one is n.
So it looks like you're actually got a different physical array for each level, which is the superscript. Do you need to do that, or can this work in place?
I think it can work in place because you only need like every one of these lines just depends on the previous level's dependencies, and these which don't get any summation get passed through. I think every level could be done in place. Okay. Okay. So it's one of the more. So we're coming to this. Eventually, we want a work efficiency, and there is actually a work efficient parallel prefix algorithm in shared memory that achieves order n time. And the way it works is basically there's two phases. The first one is called upsweep, and the last one is called downsweep. And in the upsweep, you basically do the parallel reduction that we did in the beginning of tree summation, like this, pairs, and then distance 2, and then distance 4 for powers of 2. So this is upsweep. It ends here, and this is like the code for it. You sum up left and right are becoming powers of 2 farther apart at each level. So that is n work because you're doing n summations, like order n summations at this level, and then they decrease asymptotically as you go down. Yeah, and then the harder part, I guess, is this downsweep, which is you take the partial sums that you computed during the upsweep. So in the upsweep, some of them are right. Only one of them is right, I guess. Two. The last one and the first one are right, and maybe this one is right. Some of them are right, actually. Like 7 is right, but actually, the first half is correct in the upsweep because you're kind of like doing the tree on the first half, and you're doing the partial sums. But the right half is not correct because it doesn't include the partial sums from the first half. So in the downsweep, you propagate down the partial sums that you computed in the first half. And this is the code. This is doing the exclusive version. But basically, you take the partial sums that you've computed in the first half in the tree reduction, and then you pass them down to the correct children that need them in the down half. And that is just the reverse of the upsweep. So that is again n work, and both have log n spin to do this tree-like summation. Yeah, this is a more concrete example. This is just tree summation. And the downsweep or the inclusive scan, you have to do the indexes right, which is like the hard part of this. But you start with distance 2, and then you take like the parent and you take the correct parents, and then you add them into this, and then now they just become distance 1 apart, and then you add the correct reductions into this. And then this is the thing that we started with. So Yeah, you can see at the end of the upsweep, 13 and 22 are correct because we started 13 and 19. This one is not right because we had -4. 19 is maybe right. No, 19 is wrong because it's bigger. The last one has to be right. Probably. Yeah, the last one is right because it's just the initial tree summation. Questions? So is it clear that this is like a constant factor off of optimal? Both. Huh? What happens? This is order n summations down. Yeah, the last one and the first one are definitely right in the beginning. The second one is also right in the beginning. This is also right, I guess. Because you compute it by, in the upsweep, you can know analytically which ones are right and wrong. Like in the upsweep, every power of 2 is correct. Because you could think of it recursively. So every subtree would be correct. And then you just need to propagate it to the things that are not powers of 2. So this one, and then these.
So can you show me the downsweep on the last slide where
Yeah, this is different because it's exclusive.
oh,
So I was just doing the other one, which is inclusive, so it might be easier to see. This is more for like the shape of illustration, but this would be the exact algorithm for exclusive version.
doesn't it seem too weird? Oh no, because then you're propagating.
Because you have to propagate 0 down. But okay, maybe let's go through this in more detail. So this is the upsweep, and this is the regular tree reduction, and you know that what is in powers of 2 is right within their subtree. Not necessarily overall, but definitely like the subtrees are correct because it's a recursive tree. And actually the subtrees on the left are also correct because they don't depend on anything from the right. But the subtrees on the right are not correct because, like, for example, this is the summation of these 4, but you also need like the thing from the left. So like this is not correct, for example, because this actually needs the stuff here, but it just included these 2. This -4 is not correct because it's not a power of 2. Yeah. So yeah. So like the powers of 2 on the left side and the left half are correct because they don't depend on stuff in the right, but it's not necessarily true that the powers of 2 on the right side are all correct because they may depend. Here, 0, 1, and 4 are correct. Or 0, 1, and 3, I guess. 0, 1, 2, 3. They're powers of 2 if you count from 1, like 1, 2, 4. Yeah. So these are correct because they're this subtree. But however, like these are not correct because even though this one is like this one, I guess, is a power of 2 within this subtree, it doesn't include the stuff in the left subtree because it's lower in the tree than, like, we summed it here, but actually it depended on this summation as well. So we're gonna basically push, in the second half, we're gonna like push this down. And then the last one is correct because it's just the full tree. So you don't need to push the last thing down because nobody else would depend on that whole thing. But you are going to push, like, for example, this down. Because like the stuff here depends on this. And because like due to the distances, you may not push 37 directly down because you actually want like 37 and -4. If you did 37 plus -4 plus 6, then you would get the correct thing here. And we did the partial reduction already for -4 and 37. So basically you want to push those 2 down into 6. And then how you calculate the indices, there's pseudocode. Maybe I included it on the next slide. But the high level idea is, like I said, you take these partial summations. Like here, we take 37 and minus 4 because this one is going to depend on those things. Basically, you can express every partial summation that anything that is not finished needs in terms of like the power of 2's that you've already computed or will compute when you push things down. Maybe this will clear it up. So this is the pseudocode. You go up to log n, you do the parallel 4 of your pairs at each level, and then you do this, you do the summation of like the immediate neighbors, distance 1, distance 2, distance 4, and so on, like that. And then in the down sweep, we're not pushing the final version or the final element because you don't need the entire summation, but you do need like this halfway point. This halfway point needs to get pushed down to the right half. So you're gonna push it down distance 4, then you're gonna push it at distance 2, and then 1. And then this way as well. Yeah, and then these also need to be pushed because there were not powers of 2 in the first half. Like the powers of 2 in the first half aren't correct. So you need to fix them up by pushing down the partial sums. Questions?
Are those also on the down sweep showing adding the thing with next by the diagonal and the thing right above it?
Yes. Yeah, exactly. Yeah, so this addition would be like adding these two, and then this addition would be like adding these two. And yeah, so I guess one way that you can, one example would be like this one. On the upsweep, we calculated this, which is these 4 elements, but we need the first half to get the correct partial sum. So now in the downsweep, we're going to push what was in the first half down into here. We have already calculated the subtree, and now this is the correct sum for this entire thing. Questions? Yeah. Okay. So the work in the span, I think I already gave them. The work is n, it's like a constant factor of n. The span is defined by this recurrence, which is log n. And it was a constant factor in the span compared to Hillis steel, because you have to do up and down in this one, but in that one you just have to do up. Questions?
The application of prefix.
We will do that in the second half. There are so many. Yes.
And why did you do the first one? Why is
Because you do it, well, you could just do it analytically also, because there are log n levels, and each one, yeah, I guess if the inner loop is order 1, or even if the inner loop is log n, there's only one that is log n, but you can also do it with this recurrence because the problem gets cut in half every time you go down in the upsweep, and then there's like a constant factor because you can apply this recurrence both in the top half and the down half, upsweep, downsweep, so there would just be 2 times this.
would it not be log squared? There's parallel.
Yeah, I guess this would be log squared of n in the binary forking because each one would be, yeah, because this would be like size n and minus 2 and so on. I guess this is in PRM.
We talk about PRAM ever? I feel like we just like mentioned it once and then it's like, oh, but we'll just throw it in.
Yeah, we mentioned it. I guess PRM is just easier. Like binary forking is when you have log n in the span for the loops, and PRM is just like you can do the loops in one. So the spans are most a log factor from each other. Questions? Yeah. So as I said, there are so many applications for prefix sums. Actually, like really nice applications. And it might be like prefix sum is kind of like this canonical parallel algorithm. If you have to learn one parallel algorithm, it should probably be prefix sums. Okay. Questions? Okay. So that was for shared memory, and then we're going to do a distributed memory version, which uses similar ideas, but is slightly different because um, you want to break, like at a high level, you want to break up the problem into n over p size in distributed memory because, like we said in the beginning, if each element has a different processor, then the communication cost dominates the entire thing. So you want to do like subproblems and then solve like smaller problems through communication. Okay, so we're going to do divide and conquer. The base case is simple. We started with x0, x1, and we want to sum s0, s1. So you just sum x0 into s1, or x0 and x1 into s1. Divide and conquer. So you have n processors, and let's divide them in half. Let's say you have one processor per element. For simplicity in the beginning, we're going to divide it in half, and then assume that we have an algorithm to solve prefix sums, because that's how recursion works. Yeah, so assume that we had an algorithm to solve prefix sums. So on this left half, we would get the correct prefix sum. We get x0, and then the last one, sum x0 up to x minus x n over 2 minus 1, which is the elements in here. In the right half, because we don't know, because this is distributed memory, we don't know what's in the left half. So we can only sum xn over 2, xn over 2 plus the next one, and so on up until the end. And basically, the hard part is that we want to combine, like, if you could propagate this last element into each of these, then we would be done. Right? Does that make sense? No, these are all correct. We assume that we have a recursive algorithm to solve prefix sums. So we could use the previous one. However, the previous one depends on every element being on a different processor. Like if you implemented that in distributed memory, it would not be good because in distributed memory, you need to cut up the problem into like size n over p to reduce the communication. And so like the previous one, the upsweep and the downsweep was on individual elements. Yes. So here, like this is the first step of the, I guess, the first level of the divide and conquer, which you will come back to when you unwind the recursion. And if we did have a solution to prefix sums, we would have these things on the two halves. And we're just trying to combine the two halves, but you could apply this combining idea to any level in the recursion.
That would have correct if that was the only array.
Yes. If the right half was the only array, it would be correct. And if the left half was the only array, it would be correct. It happens to be that in the overall thing, the left half is also correct. But in the overall thing, the right half is not right because obviously you need the left half. And this happens to be the sum for the left half. So we do actually have it. We just need to push it there somehow efficiently.
We just stick it into half once, or do we keep doing it?
We keep doing it. So this is like the first level of the recursion. And you can imagine like there would be an entire recursion tree down here. And then if you had an algorithm to combine the two halves, you could apply that technique in every level of the recursion. So you just have many halves. And then in the end, you would get these two halves again when you come back up. Okay. Yeah, so we want to, like I said, we have already the correct sum that needs to be pushed into the right side. We just need to efficiently push it into the right side. We can broadcast it into the right side. You could just like communicate that one element into every processor in the right side. And you could do that recursively. It takes log n to do this broadcast. You can express this as a recurrence. You have n processors, n problem size, n processors, and then you cut them both in half at each time.
So should it be 2 times t of n divided by 2, n divided by 2, calling problem size n divided by 2 instead of just 1?
But they can be done in parallel.
Okay.
Yeah, you can do the broadcast in parallel, or this. You can do every level of the broadcast in parallel, I guess.
We left some first, and then we added to like all the elements to the right.
Yes. So this is assuming that you have already solved the left half. How long would it take you to push the last element in the left half into the right half?
Okay, so we're just not going to left.
Yeah, we're just gonna assume that we have the left half for free. We're gonna simplify it.
What does n mean?
And here, for ease, we set n equal to the problem size and the number of processors.
Are they the same?
Later on, we will make p much smaller than n, but to illustrate like the recursion part, we can assume that we have processors equal to n in the beginning. And then later on, we want to, of course, in general, like the problem size is usually much bigger than the number of processors. So eventually, we're going to cut down the number of processors.
There's even just like the time for the entire problem, or is it just for the broadcasting?
This is the time for the broadcasting. Because I claim that the broadcasting is the dominant term for the time.
Like, so is this not like the formula for the entire problem's time though? Like the log n is just the broadcasting at each step, and then just go down and break it up. And if you have like two base cases, then you just broadcast as a bidder.
Yeah, exactly. Yeah. So in this one, like, I guess you could count maybe the summation also in the log n, but the summation cost is much smaller than the broadcasting cost. So the total time is dependent on this broadcasting time. Yeah. So that's fine. But ideally, we would like to do better. Can we do better? Like, we want to make it log n. Because this is the time, like, this is the time that it would take us to do a tree summation. So we want to match tree summation time. And there's kind of cute trick, which is that you can actually do it in log n time. But in some sense, to do so, you want to compute more. The issue in the previous version was that only one processor held the entire sum on the left half, which is why the broadcasting time took so long. But at a high level, what we're going to do is we're going to compute the total sum on every processor in the left half, and also the right half, like recursively. And then we can do some pairing of processors, like there's an equal number in the left half and the right half, and if you just pair them 1 to 1, you could push the left half summation from everyone into their partner on the right side. Yeah, so the idea is to compute the total sum on every processor on the left side, and then in addition to the prefix sum on the left side. And I'm going to show pictures. So this is the beginning. We're going to keep 2 elements per processor. We're going to keep both black is the total. I think black is the prefix sum and red is the total sum. And in the beginning of time, you initialize them all into the element that you have. Okay, this is just so we first solved problems of size 2. This is the recursive base case we had in the beginning. You just push the left side into the right side. Now the total sum and the prefix sum are the same, 3 and 3. And so if you push from the left, we're going to add the total sum from the left side into both the prefix and the total variables on the right side. And the weird thing that we're going to do is that we're also going to push right to left. So we're going to push 2 here into 1. And we're not going to update the prefix because, of course, the prefix here does not depend on 2, but the total sum does. We're going to compute 3. And so if you're coming from the right, you're going to add the total sum into the total sum from the left. If you're coming from the left, you add into the prefix and the total sum. So you're doing a little bit more work than what you might naturally think to do, but you could do these 2 in parallel. Because like if you have a hypercubic permutation, like we talked about last time, these are paired and then they don't conflict with each other. So you just push them and they can be done in parallel with no extra time. Yeah, so you do just the same here. Again, like you push 3 into 4 and now you got 7. push 4 into 3, and you keep 7 as the total sum. And so on. So now the total sum for each of these problems of size 2 is like the sum of the two pairs, and the prefix sum is also correct for problems of size 2. Questions on this part? Right. So now we're going to do the same, but now like rather than distance 1 apart, we're going to do them distance 2 apart. So we're going to push this total sum 3 into this total sum, or into this total and prefix, because like you need the sum of these two elements to go into the prefix of these two elements. So that's why you're going to push them. You don't need to keep pushing this because you've already pushed this to the right. So now the total sum is this 10, and then this is now the total sum in this entire first half. And then you're going to do the same. You're going to push to the left. So you don't update the prefix here. You just update the total sum. You always push the total sum, and you always update the total sum, but you only update the prefix if you're pushing from the left. And we're going to do the same on the right half. So now this total sum is the sum of all first 4 elements for the first half, and then this total sum is the sum of the second half. And the prefix is also correct down this half. Like the prefix, if this was the only list, this would be correct. And if this was the only list, it would also be correct. Okay, and then now it's the same. Push from the left into 4. And now the total sum is 36, which is the sum for the entire thing. And you update the prefixes accordingly. And this is right because we had the total sum in the first half, and we had the correct prefix sum in the second half. And this is what we were trying to do in the beginning. Like we needed to broadcast the sum of the first half into every element into the second half. And that is what now we are doing in unit time, because everybody owns the total sum in the left half. And then same the other way, you're gonna get the total sum because like this happens to be the end of this illustration because we ran out of space, but like we would need to do this if there are more levels of recursion. And each of these levels, and you can see like there are log n levels because we're increasing by distance by powers of 2 every time. And every one of these levels, like all of the processes are paired and there are no conflicts. So each of them can happen, like all of the communication can happen in parallel. You need that because let's just look at the last level. Like red is the total sum. And what we needed, like, do you remember when we had the two halves? What we needed like S of n over 2 to be pushed into every element into the right half. And now this is what we're doing. Everybody has Sn over 2, and you're pushing it into every element in the right half. This is the right half. So at this point, the right half has, like, this is like the two halves that we had in that initial illustration. This is like the correct prefix starting from here. And then to get the correct prefix overall, you need to push in the total from the left half. Sorry? The 6? This 6 came from, we pushed the total sum here into the prefix. So black is prefix and red is total. And we are always pushing total sum into total sum. And if we're coming from the left, we also push it into prefix.
We're using not the distributed one, the shared one. Would this still work? And why don't we just do this on both distributed and shared?
You could implement this in shared memory. Why would you not? Because you can do more efficient things in shared memory. Like this thing you mean? Or so this, remember that communication you can only send one word. Every processor can only send one word at a time, and receive one word at a time. And so one processor owns this summation, x0 up to xn over 2. And now every processor on the right side needs this term. So like, but it would take in serial time, or yeah, it would take, you have to keep pushing it out from the source. But however, now, because we did this pairing, like everybody on the first half owns it, so you can just do it in one step. You could do it in, I guess, like kind of like log, because you can imagine like if you sent this to somebody here, then they could send it to somebody. And then so on, like the number of people who have it would be exponentially growing, but still it would be more than one. Forward? Yeah. Yeah.
Could you talk about how you map this?
Yeah, so for the initial illustration, we're just going to map one element to one process, but in the next step, we're going to map more elements to one process because, of course, like it's not realistic to have one-to-one.
So each line is
Yeah. So in this very simplified version where we have processes equal to element problem size, each line is a communication. But in the next steps, we're going to put more elements on one process because even as we said in the beginning, just for some, like you can't, if you did this, like the communication would dominate.
How do we analyze that if one type of algorithm is better for shared versus distributed?
You can analyze the communication cost, like using tau and mu for any algorithm. Like you could implement upsweep downsweep on distributed memory as well. The initial version of upsweep downsweep, like it would require log n runs of communication. And we're going to modify this to reduce, like we don't want log n levels of communication, we want like log p levels of communication, where p is smaller than n for distributed memory. And so we're going to have to modify this algorithm to put chunks of elements on every process. Questions? Okay. This is the pseudocode. I'm not going to go through it. It's basically what we just did. Yeah, so next, like I said, we're going to do what if n is larger than p, because we made this assumption that is somewhat unrealistic that n is equal to p. Okay, so it's like this. We're going to cut up cut up the problem size n into n over p size pieces. And then we want to compute the correct summation on each one. And we could apply Brent's lemma in the beginning, and then we would get time. So it's log n to do the entire thing on n processors. With Brent's lemma, we would get n over p times log n. However, we want something even more efficient than this. We want like n over p. So we're going to have to adapt the algorithm. Okay, and at a high level, this is how it's going to work. We're going to compute the prefix sum locally on every processor, maybe with upsweep downsweep, like maybe with a shared memory algorithm like we did in the first half, or serially, just something efficient. And then we're going to perform parallel prefix using this algorithm that we just did of like the left and right pairing. And then we're going to add the result of that parallel prefix on the processor to each of the local sums. So basically, like if you come back here, each of these is separate, but here in the second half, we want S3 because we need, like, once we compute the local prefix sum here, we would want S3 to push into all of these. And then here, we would want S7, the correct S7, to push into all of these, and so on. So that's how it's going to work. And then the computation time would be n over p, which is the time to perform the local prefix sums, plus log p, which is the tree reduction on the processes. And that is more efficient than n over p log n, which we would get with Brent's lemma. Communication time is tau. This is the number of levels of communication, log p levels of communication. And tau plus u multiplied by this. Previously, I think we had used bandwidth as mu. You could sometimes, for convenience, people also like to avoid doing 1 over mu, they just write mu. But in the exam and in the homework, I would clarify. You can use like, as long as you specify like your units for mu, just depends on like, for convenience, sometimes this mu is in seconds per byte rather than bytes per second. So you don't have to do division, but it's the same idea. Okay, is this right?
Right, and you put like the second block, right? To add the results of each prior parallel prefix all of them later.
Well, we kind of tried to do that here, like in the, sorry, here. We take the last element on every, let's go back to this picture actually. We take the last element on each one of these, and then we perform prefix sum on those. And that is right for this one, because, actually, no, it's not even right for this one. It's right for none of them, because what you actually want is not the last one. You actually want like, because you're not trying to add S7 into here. Like if you did prefix sum, and this, like, imagine a tree on these elements. Yeah, you want to add S3 to S4 and like S5 and like this. And you want to add S7 like this. And you want to add 0 to this, right? So what you actually need is exclusive sum on the outer part. Yeah. So in the initial part, if you use inclusive scan on the tree, you would be adding S3 to P0. You'd be adding S7 to this part, and so on. And that's not what we want, of course. Like we don't want to add this, we want to add this. And that's why we need exclusive scan, because exclusive scan ignores like, it doesn't include your current element. It only includes like the previous elements.
Guessing it's doing this just to kind of serialize the finding the local prefix. It's possible to add the last or like do it more in parallel. Like if you add S3 on all of the P1 and then S7 all of the like you have to do that in parallel for each process or in serial for each process.
Yeah, but you had to do n over p time to compute the initial prefix sums anyway. So this is not, adding something to every element is not more expensive than computing the initial prefix sum, like because you had to do them locally to begin with. You could do also that in parallel, like we just did in the first half with the shared memory versions. You could implement that on each process. No, P0 is supposed to add nothing, because like if you had already correctly computed this prefix sum, that's it, like for this part. So, and then in this part you need S3, and in this part you need S7. But if you do normal inclusive prefix sum, you're gonna get S3 here, S37, S7 here, S11 here, S15 here, and you don't want to add S15 into these. You want to add like S11. So that's why you need exclusive sum, which is not including yourself.
You just like add as podcast.
Like you broadcast this into here, but you don't have this. Like once you compute the local prefix sums, you don't actually have the correct S8. You only have the correct prefix. You have like X8 here. You have X8 plus X9 here. You have these 3 added here, and then you have these 4 added here. So you need to do the tree. You need to do the prefix reduction step to get the correct S8, which includes the prior stuff, or I guess S7, which includes the prior stuff, and then you're going to add S7 into these elements.
I'm a little lost though.
These are processors. Sorry. So there are 4 processors here. Yeah. So I can say it again, like here, to get the correct, so when the first step is to do the local reduction on each one. And so if you just look at this one, for example, you would get x12. Here you get x12 plus x13 here. Here you get these 3 summed up into here, which obviously is not right in the end because you want all the previous stuff. And everybody else would also do like the same thing. And now only the first chunk is right. It doesn't depend on any prior stuff. So you need to, somehow everybody has to get the last element on the correct last element on the previous one. Once, like, but after you do the local estimations, like this is also not correct. And this is also not correct. You need to do the prefix reduction first to get what is correct here. And then you can do what we did to push it into the right side. Questions? Okay. Yeah, so we do the exclusive scan. Like I said, you don't actually add the total sum into everybody. You just add, you initialize with 0 rather than initializing as your own element, and then that's how you get the exclusive scan. And this is just the same like pairing that we did previously. Yeah, so if you just use inclusive scan, everybody gets all elements up to and including yourself. So here, like for example, you get 36. But now the problem is like none of the previous, like this P3 does not need 36 to push into all of its own elements. It needs actually like what is the sum of all the elements prior. So so you have the prefix. So this is like the local prefix sum. This is the first step, 7, and then you add 7 and 8, and then you get 15. And now you take the last element, and you take the last element on each processor, and then you do like the pairing thing that we just did, and then you would get, this is the correct prefix sum that you get when you take the last element on each processor. But however, like these are not the elements that each of these processes needs to put into its own elements. Like this, like you have this correct prefix sum, but you actually need to put in 21 because 21 is the sum of the previous elements. So you want to end up with 21 here rather than 36 because you want to get what you are going to push into your own local elements.
What problem does this solve that the previous way? Like, why does this work on P less than N processes and the previous way didn't?
It does. The previous one does work on P less than N. Like you can simulate, of course, the previous algorithm with N processors on P processors, but it's inefficient. So that previous algorithm on N processors was log N time. Using Brent's lemma, you can simulate P less than N, and the work would be N log N. And then just you divide by P to get the time on P processors. But we want better than this. We're going to get N, with the next thing that we just did, we're getting N over P plus log P, which is less than this.
How is the other one faster then? Processes.
How is this, like this local summation thing faster? Yeah. Because the computation time is N over P because it has less rounds of communication, basically. The previous one, the first one that we did had log N levels of communication. This one has log P levels of communication, plus the local reduction. Yeah, you still have to do like log P. These log P rounds still have to count in your computation time. but the communication time doesn't count the n over p, but it does count the like the communication constants.
So you're saying that with the other, sorry, just with the exclusive scan approach, we're updating the element we need to add directly from the prefix sum rather than having the total prefix sum and then trying to update that separate value separately.
Exactly, yeah. You want to exactly. So look at this picture. Like you want to end up after this prefix sum, you want to end up with the element that you're going to push into all of your own local elements. But however, with inclusive scan, you are not getting that because like just look at the first one, you get 3. You're not trying to push 3 into 1 and 3. You're already finished here. You want to push 0 into it. And here as well, like you're not trying to push 10 into here. You're trying to push like 3. Yeah, 3. Sorry, into here because you're trying to get like the sum of these two. So that's why the initial regular inclusive scan is not going to work because then you have to do like additional shifting and stuff. So the point of using exclusive scan is just to end up with what you wanted to push into your own local stuff. Good. Okay. And then there are a couple of things that we didn't talk about, like what if n is not perfectly divisible by p, and what if p is not a perfect power of 2. This can be easily fixed. If n is not a perfectly divisible, you just add one more to some of them. It goes away in the go. And if p is not a perfect power of 2, basically you pretend that you have the next power of 2 up number of processors, and then you just ignore like the half that you don't actually have. So this is a picture. Let's say you actually had 5 processors. You pretend that you have 8, and then you run the algorithm as if you had 8, but then like this line is just telling you what you actually have, and then you just ignore like anything that would come to and from like the part that you don't actually have. Questions?
Do we not get the data beyond the line, towards the right of the line? Do we not get that data?
So this is like you don't actually have, in this example, like we have 5 processors, 1, 2, 3, 4, 5, but this is just, we described an algorithm for a power of 2 processors. And so like we can simulate the algorithm on the next power of 2 processors, but we don't actually have 8 processors, we have 5. So you have an algorithm described for 8, so you just ignore the steps in the algorithm that would correspond to any of the 6, 7, 8 processors.
Suppose we did have n processors, would it sometimes be advantageous to use fewer than n processors?
Yeah.
Or would it
Yeah, you probably would not want to use n processors just because like you can kind of think of it as like the work per unit in some sense. Like the work per element in the prefix sum is relatively low. You're just doing constant amount of work per element. So like to make it worth it, like the work per element has to be comparable or more to the communication time.
So let's say we had, in this example, we had 16 elements.
Mhm.
And then we really only have 5 processors, but we're assuming we have 8 processors. How would we distribute the 16 elements across the 5 processors?
You would do 3 on each, and then you might put one more here, or 16 elements, right?
Yeah.
So like 15 is divisible by 5. So you would put 15 divided by 5 is 3, so you would put 3 on each one. Then you have 1 left over, so you could just put 1 here. It doesn't really matter if the only reason that would, it doesn't really affect the parallel part, because the parallel part is just doing reduction on 1 element per processor. It only matters for the serial part when you, or like the local part when you do the local reduction, and it just needs to go over the right elements in your local reduction. But on your local part, you would know how many elements you have. So, and then you're guaranteed to like only get at least 1 more element on the processors depending on the imbalance. So each processor is guaranteed to have at most 1 more element than the minimum number of elements on any other processor. Because that's the way mod works. Like you would get less excess than the number of processors than you have, and you just distribute the excess that you have, like one per processor arbitrarily. But it doesn't affect the parallel reduction part, it only affects the local part. And the imbalance is not high, it's just one more element maybe. Make sense? Cool. So I guess maybe I can just spend the next lecture doing this, but I want to do like a couple because I think that these are cute actually. So here's some applications of prefixum. There's a question earlier like, why would you ever use this? This is actually how you add elements in log n time, or this is how you add integers in log n time. You can do polynomials, you can solve recurrences. Rate extort is based on this, or can be based on this. You can do applications in image processing, linked list traversal. There's like tree algorithms that are based on something like prefixum. So many. Like I said, if you learn one algorithm in this class, it should be prefixum. Okay, so to start with Fibonacci. So Fibonacci is this recurrence, f of n plus 1 is f of n plus f of n minus 1. And you might think that this looks serial because it depends on the thing right before it, f of n and then f of n minus 1. However, you can recast this into a simple matrix multiplication. This f of n plus 1, f of n, and then like you do this horizontal and vertical multiplication to get the correct recurrence. And then you have a base case somewhere. And then you can use matrix multiplication as your binary associative operator. And then you could get the correct answers by performing prefix sums on these. This is always going to be the same for any f of n. And so to get this, you can imagine multiplying your matrices left to right. And then you can do so using parallel prefix. So, and then the upper left is just the correct answer for fib. Yeah, so for applications, like in the exam, I won't ask you to like give me the algorithm for parallel prefix again, because there's not much point. And you don't have to like tell me the time for parallel prefix again, because we just went over it. But on the exam, and also you'll see on the homework, the questions will be like more which part of the algorithm would need parallel prefix? Like how can you cast this into parallel prefix? Yeah, and you can also do this for any linear occurrence. It doesn't have to be this particular set of constants. This turns out you can do random number generation this way, for example. Yeah, you could do operations on arrays. So this is one really common trick that actually I use all the time because sometimes you need this. Okay, so you get an array, which is size n. You get a, and then you get a set of flags, b through bn. So these are the same length. And they're either like true or false. And true means that you want to keep that element. And then you want to output like an a prime containing only the elements that saw true. Like you would want to keep 2 because this has true, but you would want to remove 4 because this has false. And you're just trying to efficiently create this a prime with only the elements that correspond to true. And of course you can do this serially, like left to right. You would just copy in the elements that saw true left to right. But you want to do it in parallel. And the problem with doing it in parallel is like, how do you know how to get it packed into the left? You need to know how many elements came before you, or how many true elements came before you. You can't just copy this, for example, like you see true here. This is in position 0, 1, 2, but you can't just copy this directly into position 2 because now you're going to have empty space. So you want to like pack all the real elements into the left side. And the way that you're going to do that is you do prefix sum basically on B, where B is like zeros and ones. And then what you get, you do exclusive sum. And then what you get is like the location of the destinations. So like I said, you convert true false into 1 and 0. And then you perform exclusive sum on this thing. And now this is 0, this is 1, this is 2. And this happens to be where you want to copy in the corresponding elements in A into this thing. And you know how many, you even know how many, the size of A prime, because that's going to be the last element in the exclusive sum.
Which is like what would be the rightmost of each element? Like in this case, you choose the rightmost one, right? Because that's when it's actually worry about. Yeah, like choosing the right one.
Well, you get the rightmost number for free when you do the prefix sum.
So, but I'm saying like you can still have to serially iterate over mean, right?
No, you can do this conversion from true and false into 1 and 0 in parallel. Like you would make a parallel 4, and then you would just say like if it's true, put a 1 there. If it's false, put a 0 there. Or if B was already like an array of ints, like you would get this for free. You don't even have to do this conversion. And then you perform parallel prefix on this, and you would get this B prime. You can do parallel prefix in place too.
Oh, I meant to say from the compression step. I get the prefix step part. I'm saying like so now you have two ones over here. How do you know that you actually want index one and one or index two and one?
You do a parallel 4 over this B, and then if you see true, then you look up into B prime, and then you do like A of B prime of I equals, sorry, A prime of B prime of I is A of I. Yeah, so that is how you get them all in the right place in parallel. Yeah, exactly. You need to be really careful not to serialize any of the steps because then there's no point in parallelizing the first one. Okay.
So how do you know like that? So I imagine you don't know that like when you have figure out that your first element is going to go into index 0 and A prime or whatever, you don't know that your thing is going to your final array is going to be 3 at that point.
You know that the final array is going to be 3 because that's your last element in the exclusive scan.
Well, like you don't necessarily have that.
You don't have that before you perform the prefix sum.
So, I mean, this is just like kind of a detail thing, but like you don't. When it says allocate array of size data, it just makes me think that you like need to like do the whole thing, and then you allocate through it, and then you go back and like find your elements actually going through it.
You need to do. Can you say it again? You need to do the prefix sum before you can allocate the size.
Right.
But you don't. After you do the prefix sum, the only step is copying in.
So how do you know? Like then you have to look back through prime to find where the copy stuff to from. Right?
Yes, you keep around B prime, but you're trying. This is A prime.
Yeah.
Yeah, from B prime, look at the last element, and then you get the size of A prime,
Right.
and you allocate A prime, and then you assign them according to this, which is
Oh.
yeah. This is the outer one is parallel, and this is just saying like you know which ones to copy because they had some. Oh, I guess you need to keep around B then because you just look at what was true in B, and then you look at what you got in B prime, and then that is your destination index for the corresponding element in A.
It looks like you don't need to keep B because you just check by seeing.
Ah, yeah, this is like if you saw a change. Yeah, good point. And that's in the pseudocode. So, yes, good point. You don't even need to keep around B. Even better. Yeah. So I thought this was cute because like it kind of looks serial because you need to know how many things came before you, but this is a nice application of parallel prefix. And actually, like this comes up a lot. Maybe it's because I do data structure, so this does come up a lot for me. But nice trick. And I think I'm out of time, so I will continue this next time. Thank you. Oh yes.
Shouldn't the loop be from 0 to n minus 2 because if you take I to be n minus 1, then I plus 1 becomes n and it runs out of.
Yes, it should be. Yes, exactly. It should be n minus 2. Or maybe like it should, because you still need to evaluate n minus 1 to see if you need to copy it in. So maybe like for n minus 1, you just don't do this condition. You just check some other condition, like if it changed from prior or something. Thank you.